Now that we know terms related to the study of nuclear chemistry, we can begin to write equations for the different types of nuclear reactions. There are four main types of nuclear reactions. In all of these situations, the nucleus is trying to become more stable by regulating the ratio of protons to neutrons. The first type of reaction is alpha particle emission, where a nucleus emits an alpha particle. In other words, it loses 2 protons and 2 neutrons. Next we have beta emission, the conversion of a neutron into a proton. The opposite occurs in positron emission, where a proton is converted back into a neutron. And finally we have electron capture, where a proton combines with an electron to form a neutron. We will first begin by looking at alpha decay. The alpha particle can be written in one of two ways. On the left you see the traditional Greek letter alpha, with a mass number of 4 and atomic number of 2. Since the alpha particle is essentially a helium nucleus, on the right you see the symbol for helium with the same mass number and atomic number. For our first example of alpha decay, we will use polonium. Polonium is element number 84. So we write the nuclide symbol for polonium by writing the symbol for the element and the atomic number in the lower left corner. This particular isotope of polonium has a mass number of 206. We write that in the upper left corner. We then draw an arrow. Since this is undergoing alpha decay, it is going to release an alpha particle. So our first product is the alpha particle. Remember that you can use either the alpha symbol or the helium symbol. We then need to figure out what is left over in terms of protons and neutrons. We do this by subtracting the mass numbers and the atomic numbers. 206 minus 4 will give us 202. That is our new mass number. 84 minus 2 gives us 82. That is our new atomic number. We then look up element number 82, which is lead. And we now have a balanced equation for the alpha decay of polonium-84. As we go through the next example, please take time to pause as you try to attempt each step of writing the nuclear equation. For the first step, we want to write the equation for the alpha decay of uranium-238. So we will need to first write the correct nuclide symbol for uranium-238. Go ahead and see if you can write the correct symbol for uranium-238. Check your symbol to see if it matches mine. If it does not, go back and make sure that you're using the correct atomic number for uranium. The 238 mass number was given to you. Now draw the arrow. Since this is alpha decay, we want to write in the alpha particle. Please pause the video and do this now. Next, we will write in the alpha symbol. We now need to come up with the correct particle that is produced from this alpha decay. At this time, please pause your computer and see if you can come up with the correct symbol with correct mass numbers and atomic. Your final equation should look like this. Uranium-238 decays by alpha decay to produce thorium-234. The next type of decay, beta, can be represented in one of two ways. On the left is the traditional Greek letter beta with a mass number of 0 and an atomic number of -1. Since a beta particle is essentially a high-speed electron, we can also use the symbol for electron, E, with the same mass and atomic number. With beta decay, we will once again have an unstable isotope of a substance, in this case antimony. This is antimony 124. When it undergoes beta decay, it's going to release a beta particle. The beta particle will then be written as one of the products. We do the same thing to find the new mass number and atomic number. Subtract. So 124 minus 0 is 124. 51 minus a -1 is actually 52. Remember your rules for adding and subtracting negative numbers. We then find the symbol for element number 52, which is Te, tellurium. We will now have you do an example where you will pause the video as needed. We are going to look at the beta decay of iodine-129. Please write the symbol for iodine-129 now. We now need to write in the symbol for beta decay. Pause your video and write in that symbol. We now need to figure out what our new mass number and atomic number are. Pause your video and fill in those numbers and look up the corresponding element. Following correct math, we should have a mass number of 129 and atomic number of 54, making our substance xenon. Please keep in mind that through these nuclear decay processes, we're talking about individual atoms whose nuclei are unstable. When this happens, an atom is undergoing this change, not the entire elemental substance. Next, we have positron emission. Positron emission is essentially the opposite of beta decay. The positron particle looks like this. The positron particle differs from the beta particle only by the fact that one now has a plus sign in front of it. Please be aware of this small difference. For our first example of positron emission, we're going to look at magnesium-23. Notice we wrote the mass number of 23 at the top left corner and the atomic number of magnesium-12 on the bottom left corner. Since it is undergoing positron emission, we note that that is being emitted as a particle or as a product. So we then draw in the particle for the positron. Much like the previous examples, we now need to figure out the new mass number and the new atomic number. We subtract just as with previous examples. 23 minus 0 is still 23. And 12 minus 1 is going to be 11. We then look up element number 11, which we see is sodium. Let's now try an example of positron emission. We're going to use manganese 50. Notice I said manganese, not magnesium. Please pause your computer now and write the nuclide symbol for manganese 50. Your symbol for manganese 50 should look like this. Now you need to write the symbol to show that a positron particle is being emitted. So we next draw an arrow, and then we will write the positron symbol. Please pause your video and do this now. Your positron symbol should look as this. We now need to figure out the new mass number and new atomic number so we can figure out what atom this nucleus has converted into. Please pause your video now and determine the final part of this equation. You should see that chromium-50 is your new particle, plus the positron particle. Next, we're going to take a look at electron capture. The three previous examples all showed decay or emission of a particle. In electron capture, the unstable nucleus is going to capture an electron. This will place the particle on the reactant side of the equation. The symbol for electron capture is the same electron we use for beta decay, with the 0 and the -1. Our first example will be krypton 81. We want to show the electron capture of this isotope. We first write the nuclide symbol for krypton 81. Since it is electron capture, we need to show the electron as a reactant. It is being captured by the krypton. In previous examples, for the mass number and atomic number, we subtracted. Since the substance is on the same side as the original nucleus, we will be adding. So 81 minus 0 is 81. 81 plus 0 is 81. And 36 plus a -1 is 35. We then need to look up element number 35. Looking at our periodic table, we will see that it is Br for bromine. Now let's do an example together. Write the nuclide symbol for curium-239. Pause your video now and do this. Your symbol for curium-239 should look like this. Please pause your video and show now the electron capture. Remember that electron capture, the electron should be written on the reactant side, so it should look like this. Pause your video again and show the new product on the other side. Your product should be americium-239, which has an atomic number of 95. Please notice that on either side of the equation, for all 4 types of decay, that the mass numbers are always equal and that the atomic numbers are always equal.